Alright, in today's video we're going to take a look at Coffee Cup Calorimetry and the calculations that go with it. At its simplest, calorimetry simply means to measure heat, and related is the idea of something called the specific heat capacity of a substance. The specific heat capacity is the amount of heat measured in joules that will be needed to raise the temperature of 1 gram of a substance by 1 degree Celsius, or by 1 Kelvin, which would be the same amount. For water, the value for the specific heat capacity is 4.184 joules per gram per degree Celsius. Water has a pretty high heat capacity compared to other substances. It's what helps water serve as an insulator. People live near a large body of water like a lake or the ocean. Their temperatures don't fluctuate as much as people who live inland because of this high heat capacity. Another way to put it, imagine you had a container of water, a beaker of water, and you had just started heating it with a Bunsen burner. Well, after a minute or two, you would not expect the water's temperature to have risen that much. On the other hand, if you were to take a piece of metal, say iron or copper or aluminum, and put it directly in the burner flame for the same period of time, you'd expect that object to become very, very hot pretty quickly. And that's because the metals tend to have lower heat capacities. So the same amount of heat would cause the temperature of the metal to rise dramatically, as opposed to the temperature rise in the water. One simple calorimeter, a version of a calorimeter, is called a Coffee Cup Calorimeter. So we take a couple of styrofoam cups nestled together. 2 of them is better than 1, just to provide better insulation. You put some water in the cup. You measure the temperature inside the water using a thermometer. You have an insulated stopper or perhaps another piece of styrofoam on top to further protect heat from escaping or entering the calorimeter. And then there's some kind of metal rod which will be used to stir the reaction mixture inside the calorimeter. So the basic idea is we're going to measure temperature changes with the thermometer and then relate that with specific heat capacity to the amount of heat being absorbed or released within the process in the cups. The simplest uses of coffee cup calorimeters would be to measure specific heat capacities of metals. So let's begin with a simple problem that reflects that. If you think you know what you're doing, pause the video and try it yourself, otherwise follow along with me. So we've got a coffee cup calorimeter with a mass of 25.26 grams, so that the styrofoam cups and their little cap on top weighs 25.26 grams. It's filled with water at 22.3 degrees Celsius, so there's the initial temperature of the water. The total mass is now 105.39 grams. A dry test tube is filled with 50 grams of aluminum metal pellets and then placed in a boiling water bath for several minutes. Now what we're doing in that step is we're heating up the aluminum pellets to be about 100 degrees Celsius. We're putting them in a dry test tube so that we can then pour the pellets into the calorimeter without getting any of that boiling water in there as well. So those hot pellets are quickly poured into the calorimeter. The cap is placed on. We stir the contents with that metal stirrer, and we watch the thermometer. We see the temperature rise to a high of 31.5 degrees Celsius. Eventually, of course, the temperature would start to cool back down again, but that's the highest temperature that it reached. We want to use that data to calculate the specific heat capacity of the aluminum metal. And in this question, we're going to assume that our calorimeter is perfectly insulated. So in other words, no heat is lost through the walls of the styrofoam cups, through the thermometer, through the stirrer, etc. That's not a really good assumption, but it's not bad for the first approximation. So what we want to do here is realize that the basic idea that I always start with is a word sentence. We have a hot aluminum metal pellet. So we're going to say that the heat that is lost by the hot metal, remember this hot metal was placed into the water in our calorimeter, so the heat that's lost by the hot metal is equal to the heat that is absorbed by the water. Then I'm going to translate that statement into what I call the MCAT formula. Heat lost, so if it's lost, it's going to be an exothermic, heat escaping, so I'm going to start with a negative sign there, MC delta T, and that's what I refer to as the MCAT formula. The mass of the metal times the heat capacity of the metal, and let me put some subscripts here. This is aluminum metal, and aluminum metal. So the heat capacity, specific heat capacity, is capital C. If we multiply that by the mass and by the change in temperature for the aluminum, we'll have the heat lost by the metal. You can see that when you think of the units for specific heat capacity. The units are joules per gram and degrees Celsius. So if we multiply the specific heat capacity by mass, that'll cancel out those units of grams, and by the change in temperature, delta T, that'll cancel out the Celsius there. We'll be left with joules, which is the amount of heat, in this case, lost by the metal. The water is absorbing heat, so we'll use positive MC delta T for the water, and I'll just use little W's as subscripts for water. Now another way to rationalize this is that the delta T for the water is going to be positive because water's temperature is rising, so the final temperature will be higher than the starting temperature, so this side of our equation is positive. On the other hand, the aluminum metal temperature is dropping, so its final temperature will be smaller than its initial temperature, which means its delta T is actually going to be negative. You couldn't have a negative equal to a positive, so this negative sign out front makes both sides positive. It really doesn't matter which side you put the negative on. I put it here just because the heat's being lost by the metal. Now, if we want to solve for the heat capacity of the aluminum, specific heat capacity, it's going to equal the mass of the water's heat capacity times the change in temperature of the water, divided by negative mass of the aluminum and the change in temperature for the aluminum. And just looking at that, the masses are going to cancel, the delta T's are going to be canceling, and so I can see I've set it up correctly. We're going to have a heat capacity units. Now, putting in our numbers, the mass of the water, if we take the 105.39 grams after it was filled and subtract the 25.29 grams when it was empty, we'll get the mass of the water, which was 80.13 grams, times the heat capacity of water, which we should just know. It's often given in the question, but we should just know that from a moment ago, 4.184 joules per gram degrees Celsius. And then whenever you're finding a change in temperature, always remember that it should be the final temperature minus the starting temperature. So the final temperature was 31.5 degrees Celsius minus the starting temperature for the water, which was 22.3 degrees Celsius. And then divided by negative the mass of the aluminum, it was 50.0 grams. And the change in temperature for the aluminum, again, its final temperature minus its initial temperature. Now, we knew that the initial temperature was 100 degrees Celsius, but it didn't explicitly say what the final temperature was. Keep in mind that the aluminum is sitting in the water, and they come to a thermal equilibrium, which means they come to the same final temperature. So the aluminum's temperature when at the end of this experiment is also going to be 31.5 degrees Celsius, and it was starting off sitting in that test tube in boiling water, so its original temperature was 100 degrees Celsius. Always take the final temperature minus the initial temperature to find a change in temperature. Grabbing your calculator and doing this little arithmetic, you'll get 0.901 joules per gram degrees Celsius is the heat capacity for the aluminum. Now, if you wanted to say Kelvin here instead of Celsius, that's fine, since the change in temperature is the same whether it's a Celsius change or a Kelvin change. Think about that for a moment. If you went from 0 degrees Celsius up to 5 degrees Celsius, your change in temperature would be 5 degrees Celsius. At that same temperature changes in Kelvin would go from 273 Kelvin up to 278 Kelvin, which is a 5 Kelvin change. So the change in temperature can be either in Celsius or Kelvin. It gives you the same change. All right. Here's another use of calorimetry, of coffee cup calorimetry. Kids often, when they first start using Bunsen burners, will ask me how hot the flame can get. Well, here's a way to do that. We can actually measure the temperature of the burner flame using coffee cup calorimetry. We've taken some copper metal. We know its heat capacity, 0.386 joules per gram per degree. We have 25.0 grams of the copper metal, and we put it directly in a burner flame. We're going to leave it in the flame for several minutes so that we can assume that the temperature of the metal is the same as the temperature of the flame. The hot copper was then transferred to a coffee cup calorimeter, in which we have 100.0 grams of water at 20.1 degrees Celsius. The temperature was seen to rise from 20.1 up to 29.1 degrees Celsius. What was the temperature of the burner flame? And again, we're going to assume that no heat is lost to the surroundings, that the calorimeter is perfectly insulated. So again, we'll start with that little word equation. The heat lost by the hot copper is going to equal the heat absorbed by the water. So for the copper, negative mc delta T, for copper, Cu, equals positive mc delta T for the water. Now we're looking for the initial temperature of the copper, or the initial temperature of the copper, which would equal the temperature of the burner flame, and that initial temperature is in here. It's inside the change in temperature for copper, which would be the final temperature minus the initial temperature. So what I'm going to do here is I'm going to start by finding just delta T for the copper. So the change in temperature of the copper will equal the mass of the water, water's heat capacity, and the change in temperature of the water divided by negative mass of copper and the heat capacity of copper. So grabbing our numbers from above, we get 100 grams, the mass of the water, 4.184, the heat capacity of water. I'm going to leave the units out here just because I'm getting a bit cramped for space. And then the change in temperature of the water, its final temperature was 29.1 degrees minus the initial temperature, which was 20.1 degrees. There's the change in temperature of the water, divided by negative the mass of the copper, which was 25.0 grams, and then the copper's heat capacity, which was 0.386. I'll leave the units out again just for laziness. So I'm going to get the change in temperature of the copper, grabbing a calculator and evaluating that, negative 390.2 degrees Celsius. So now let's remember that that change in temperature, negative 390.2, is equal to the final temperature of the copper, which would be the same as the final temperature of the water, so 29.1 degrees, minus the initial temperature of the water, which I'll just say T initial. And now rearranging that, we get T initial is equal to 419.3, I'll just say 409, well, we're subtracting with one decimal place, so 419.3 degrees Celsius was the initial temperature of the copper, and therefore the temperature in the burner flame, 419 degrees. All right, let's try another one. We're going to switch from basic physical chemistry kind of applications, physical science, to more of a chemistry example. In this next question, we're going to talk about enthalpy change. Enthalpy, we remember, is given the symbol capital H, and enthalpy change is delta H. In our kinetics unit, we called delta H the heat of reaction, and that's because, as we saw in our class discussion, if you have laboratory conditions of constant pressure, then enthalpy change is the heat. So heat at constant pressure, QP, is the same as enthalpy change. Now, if the pressure is not held constant, if you are inside what's called a bomb calorimeter, a heavy steel chamber whose volume is rigid and unchanging, and you do some kind of combustion reaction inside there, the pressure does not stay constant, but the volume does. In that kind of calorimetry, constant volume calorimetry, the heat is not equal to delta H. The heat there is equal to delta E, the change in internal energy. We're only going to restrict our discussion to constant pressure calorimetry here, where Q is equal to delta H. So we're going to use the calorimeter, which can measure heat, to indirectly then tell us delta H for a chemical reaction or for a physical process like melting or something like that, some kind of phase change or dissolving. So we've got, in this first example, 50.0 milliliters of 0.7 molar copper sulfate solution, and we're adding that into a calorimeter with 50 mils of 1 molar sodium hydroxide. The initial temperature of both solutions was 22.5 degrees Celsius, and when mixed and stirred, the temperature inside the calorimeter rose to 25.7 degrees Celsius. We're going to assume that no heat is lost, that the calorimeter is perfectly insulated. We'll assume that these solutions have heat capacities similar to that of water, 4.18 joules per gram per degree. We'll also assume that the densities of the solutions are 1.00 grams per mil. We want to calculate the molar enthalpy change measured in kilojoules per mole for the precipitation reaction that would occur when we mixed those solutions. So the copper sulfate and sodium hydroxide, in the calorimeter we're going to see solid copper hydroxide precipitating. Now before we go any further, just note the temperature change. It went from 22.5 to 25.7. So the temperature inside rose. Why would the temperature go up? It must be that this reaction is producing heat. The heat is causing the temperature to rise. So we right away know that because the temperature went up, this must have been an exothermic process. And if it's exothermic, its delta H is going to end up being a negative value. Let's keep that in mind. So we're going to say here that the delta H for the reaction happening in our calorimeter is equal to the heat measured at constant pressure, QP, which in this case we're going to say is equal to negative MC delta T. Now why negative? The water, imagine in this case we do have an exothermic process, so the delta H will be negative. In that situation, the water's temperature rises, which means delta T for the water is positive. So since this is going to all be positive, to get a negative delta H, we need to put a negative sign in front. On the other hand, imagine this had been an endothermic process. If it were endothermic, delta H would have to be positive. If delta H is positive, then this has to be positive. But in an endothermic process, the temperature would have gone down. It would have become colder, which means that the delta T would have been a negative value. So again, we would need a negative sign to make it positive. So essentially, the heat that is being lost by the process or absorbed by the process, if you want, the chemical reaction, is either going into the water or coming from the water. So we'll just use that negative sign to get our sign conventions in place. So now we'll put our numbers in here. The mass of the solution is what we need here. Now I'm going to do some mental math, but you could do this on paper. 50 mils and 50 mils, so we have 100 mils of solution total, and the density is 1.00 grams per milliliter. So setting up a single unit multiplier, you could show that 100 milliliters of solution, assuming the volumes are additive, would give me a total mass of 100 grams. So negative 100 grams. We're assuming the heat capacity of the combined solution is that of water, so 4.18 joules per gram degree. And the change in temperature was the final temperature, so 25.7 degrees, minus the initial temperature, 22.5 degrees. Grabbing a calculator and evaluating that, we get negative 1,338. I'm going to be a little lazy with my sig figs there. Negative 1,338 joules, and that's how much heat was produced by the precipitation reaction in the coffee cup. Now that number by itself really only applies to this exact situation where we mixed this chemical with this one in those exact volumes and concentrations. So that number is not very useful in terms of a universal understanding of this reaction. That's why we want to translate it from the amount of heat in this particular experiment to the amount of heat in kilojoules per mole of reaction. So how do we do that? Well, first let's realize that there was a limiting reagent concept here. We had an amount of copper sulfate mixed with an amount of sodium hydroxide. We're going to need to figure out which of those two reactants was the limiting reagent. So to do that, we'll first calculate the moles of copper sulfate, NCuSO4. It's equal to concentration times volume, or if you prefer to use a unit multiplier, go ahead and do that. Substituting those numbers, 50 mils converted to liters and 0.7 moles per liter, we can find the number of moles, 0.0, I'll just redo that, 0.035, I think, 0.05 liters times 0.7, 0.0350 moles of copper sulfate. Doing the same thing for the sodium hydroxide, the moles of sodium hydroxide, concentration times volume. I'm a big fan of unit multipliers, but this CV formula is so fundamental in chemistry, you should definitely know it and feel free to use it like I'm doing here. So using the numbers 50 mils and 1 molar, we get 0.050 moles of sodium hydroxide. Now to figure out the limiting reagent, I'm going to pick one of these two and ask myself how much of the other would I have needed to react with it. So for example, if we take our 0.035 moles of copper sulfate, from the balanced equation above, 1 mole of copper sulfate needs 2 moles of sodium hydroxide. So get rid of your moles of copper sulfate and ask yourself how many moles of sodium hydroxide would we really need to react with this copper sulfate? 2 moles for every 1. So we're going to need 0.070 moles of sodium hydroxide needed. Now we had 0.05 moles of sodium hydroxide. That means that the sodium hydroxide was the limiting reagent. We don't have enough sodium hydroxide to use up all of the copper sulfate. So therefore, sodium hydroxide is our limiting reagent. Okay, we have excess copper sulfate, and the sodium hydroxide is going to get used up. Now the reason I wanted to know the limiting reagent is the sodium hydroxide is because now we'll take our heat, negative 1338 joules, and we'll get rid of joules and switch to kilojoules. And then we'll divide that by the moles of sodium hydroxide, the limiting reagent. But we want to really not refer to moles of NaOH, we want to refer to moles of reaction. So we'll get rid of the moles of sodium hydroxide and replace with moles of reaction. 1 kilojoule is 1,000 joules. We saw in our calculation that we had 0.0500 moles of sodium hydroxide. That's how much got used up. It was the limiting reagent. And then from the balanced equation, there's 2 moles of sodium hydroxide in the equation. So we'll say that 2 moles of sodium hydroxide for every 1 mole of reaction. Grabbing the calculator and evaluating that, we get a final answer of negative 53.5 kilojoules per mole of reaction. All right, so there we first did a calorimetry question using our MCAT formula to find the heat produced or absorbed, in this case produced, in this particular experiment. We then, in this question, had to figure out the limiting reagent, which we identified as sodium hydroxide, and then we took that heat, converted to kilojoules per mole of sodium hydroxide, but then per mole of reaction. Okay, again, the 2 moles for 1 mole of reaction because there's 2 moles of sodium hydroxide in the balanced equation. If we were using copper sulfate, we would end up saying that there's 1 mole of copper sulfate for every mole of reaction. All right, so using coffee cup calorimetry to measure delta H, the enthalpy change for a precipitation reaction. The next example is another classic one for calorimetry because it involves the cold pack reaction. When you buy a cold pack, often what's inside of it is some solid ammonium nitrate, and there's some water as well inside the cold pack. When you snap the cold pack or shake it, you end up dissolving the ammonium nitrate inside the water, and as a result the temperature, as we can see, drops and it becomes colder. So in this particular experiment, we've measured out 5.44 grams of ammonium nitrate, and we're dissolving it in 150 grams of water in a coffee cup calorimeter. The temperature was observed to drop from 18.6 degrees initially to 16.2 degrees at the end. We want to calculate the molar enthalpy of dissolution for the ammonium nitrate in water, and we'll assume that the specific heat capacity of the solution is 4.18 joules per gram per Kelvin. All right. Now, what does this mean, dissolution? Dissolution just means dissolving. So our process here is ammonium nitrate solid is becoming ammonium aqueous and nitrate aqueous. That's the chemical process that's happening, or you might argue that's a physical change here. We're just dissolving the ammonium nitrate in water. So we'll again start by saying that the delta H is equal to the heat at constant pressure, and it's at constant pressure again because a coffee cup calorimeter is not a rigid, perfectly sealed device. It's got holes in the lid to allow the thermometer and a stirrer, so it's essentially open to the atmosphere. So that's equal to negative MC delta T. Putting our numbers in. Now, what mass should we use in this question? Well, the 5.44 grams was just the mass of the solid ammonium nitrate. The 150 grams is just the water. The key is at that last statement where we're assuming that the specific heat capacity of the solution is 4.18 joules per gram per degree. So therefore, since we're talking about the solution, we're going to add those two masses together to get the total mass of the solution. So negative 155.4 grams would be the mass. Keep in mind when you're adding measurements, you round off your answer by decimal places. So I'm keeping 1 decimal place in the total mass. Times 4.18, the heat capacity of the solution, and delta T, the final temperature, which was 16.2 degrees, minus the initial temperature, 18.6 degrees. And again, remember that even though it's in Kelvin in the heat capacity, it's a change in temperature, so we can use Celsius or Kelvin there. So grabbing a calculator, this works out to be positive 1,560 joules. And it makes sense that it's positive because the temperature was dropping. If the temperature was dropping, the process was endothermic. Okay, it was getting colder, so it's an endothermic process, which means that the delta H has to come out as a positive value. So now let's take the 5.44 grams of ammonium nitrate, and we want to get the molar enthalpy of dissolution. So we want this to be per mole of reaction, and we'll probably also want to convert the joules to kilojoules again. So let's figure out how many moles of ammonium nitrate we're actually dissolving. So we'll get rid of the grams of ammonium nitrate, switch to moles. I hope you realize that unlike the last example, this is not a limiting reagent question. We don't have the amounts of two reactants given, so it's actually going to be a little bit easier. And then from the balanced equation, there's only 1 mole of ammonium nitrate in the equation, so we can switch from moles of ammonium nitrate to moles of reaction. That'll be a 1-to-1 ratio because of that. The molar mass of ammonium nitrate is 80.06 grams. So that means we've got 0.0679 moles of reaction. So let's take our heat from this experiment, 1,560 joules, and we'll convert that to kilojoules, and then divide by moles of reaction so that we end up getting kilojoules per mole of reaction as our answer. So 1 kilojoule has 1,000 joules in it, and we had 0.0679 moles of reaction, so that gives me 23.0 kilojoules per mole. And again, it's positive because this was an endothermic process. Alright, this last example is going to be more complicated. I hope you can sense that just by looking at the size of the question. It's actually got 2 parts to it, and that alone would make it more difficult, more complicated. But it's also going to be more complicated because we're not going to assume in this next question that the calorimeter is perfectly insulated. In fact, we're going to recognize that some of the heat is actually absorbed by the calorimeter or lost to the air around it, the surroundings. So what we're going to do in this question is start by calculating the heat capacity of the calorimeter itself. In other words, what we're going to be doing is figuring out we're going to take into account the heat that is the heat that is being lost either to the calorimeter or through the calorimeter to the surroundings. Once we know that, we can then use it to go ahead and find an enthalpy of a reaction, in this case an acid-base neutralization reaction. So the first paragraph is to find the heat capacity of our calorimeter. We take a 93.3 gram piece of iron metal, 65.58 degrees Celsius initially, put into a coffee cup calorimeter with 75 grams of water initially at 16.95 degrees. We stir, we see the temperature rise to 22.21 degrees Celsius. We're not going to assume that the calorimeter is perfectly insulated. We know that iron's heat capacity is 0.444 joules per gram per degree. Before we go any further in the problem, let's just jump down and calculate the heat capacity of the calorimeter using that information. So what I want to do here is realize that the equation that I'm going to start with is going to be a little bit more complicated. We're going to be saying that the heat lost by the hot iron is equal to 2 things now. It's the heat absorbed by the water plus the heat absorbed by the calorimeter. And I'm going to say heat absorbed by the calorimeter. That will include any heat that was also lost through the calorimeter to the atmosphere, okay, to the surroundings. So what we have here is negative mc delta T for the iron, Fe, 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 equals positive mc delta T for the water, so WWW. And now here things are going to be a little bit different. We're not going to be talking about the specific heat of the calorimeter. It's not going to be per gram. So instead we're just going to say plus C delta T, where this C is the calorimeter constant, the calorimeter's heat capacity, and delta T of the calorimeter. Because it's not per gram, it's not a specific heat capacity, so there's no M in that last formula. So the heat lost by the metal, heat absorbed by the water, heat absorbed by the calorimeter. And now what we're looking for in this equation is the heat capacity of the calorimeter, so C calorimeter. So if you want to do the algebra first, I suppose we could rearrange all this and we could say that the heat capacity of the calorimeter will equal, if I add this to the, or subtract this rather from the other side, we would get negative mass of iron, heat capacity of iron, delta T for iron, minus M mass of water, heat capacity of water, delta T for water, all over delta T for the calorimeter. So now plugging our numbers in, we get negative 93.3 grams mass of the iron times 0.444 heat capacity of the iron. Iron's change in temperature, the final temperature is 22.21 minus its initial temperature 65.58 minus the mass of the water, which was 75.0 grams. Water's heat capacity, 4.184. I'm getting a little cramped for space. Let me just put this like this, times delta T for the water. Its final temperature was 65.58. Did I get that right? Water's final temperature, I think I might have made a mistake here. The final temperature of the iron, no, that's right. Water's final temperature is 22.21. I think I've just misread. I'm looking at my answer key here, and I think I've just misread something. So the final temperature was 22.21, and the initial temperature of the water was 16.95. So 22.21 minus 16.95. That's right. And then we divide that by the change in temperature of the calorimeter. Now the calorimeter's change in temperature would be the same as that for the water. So we'll take 22.21 minus 16.95. And now grabbing a calculator, I'm going to have to recalculate this since I think I made a mistake in my original question. So grabbing a calculator, we get negative 93.3 times 0.444 times brackets 22.21 minus 65.58, subtract 75 times 4.184 times brackets 22.21 minus 16.95 equals, and then we divide this by 22.21 in brackets minus 16.95, and I get 27.8, which is the answer I had on my answer sheet, even though I was using the wrong numbers there. 27.7 joules per degree Celsius. Now notice it's joules per degree, not per gram per degree, because again, it's not a specific heat capacity that we found. Alright, so there's the heat capacity of our calorimeter. Now that we've sort of calibrated the calorimeter, we know its heat capacity, we use it in the second part of the question. The calorimeter was emptied and dried out. Then 20.00 milliliters of 0.625 molar sodium hydroxide, initially at 21.4 degrees Celsius, and 30 milliliters of 0.5 molar acetic acid at the same initial temperature were added to the calorimeter. The solutions were stirred. A neutralization reaction happens, which is why we're going to be finding the enthalpy of neutralization for this reaction. The final temperature rose to 24.35 degrees Celsius. Since the temperature rose, we know right away that this neutralization reaction is exothermic. Its delta H will be negative. We want to assume that the heat capacity of the mixture is 4.18 and that the density of the mixture is 1.02 grams per milliliter. So now we want to find delta H for the neutralization reaction measured in kilojoules per mole of reaction. If you think you know what you're doing, pause the video and jump in and try it yourself. Alright, so I'm going to do that here, part B. So we're going to say here that the delta H for the reaction is equal to QP, which is equal to negative MC delta T. That would be for the water. And so I'm going to leave it like that, but realize it's more complicated than that. It's equal to negative, and then we have to worry about the MC delta T for the water. Plus the C delta T or calorimeter. So in other words, the heat that is being produced by the reaction, some of it's being absorbed by the water, some of it's being absorbed by the calorimeter. So that's why this is a more accurate, more precise way of doing this than assuming that the calorimeter is perfectly insulated. So putting our numbers in, we get negative, the mass of water in the calorimeter was, the mass of the solution. How do I figure that out? Well, we had 20 milliliters mixed with 30 milliliters, so we had 50 milliliters of solution. 50 milliliters, and if we use the density 1.02 grams per milliliter, we get a total mass of 51.0 grams. That'll be the mass of the solution. Heat capacity is 4.18, and the delta T, the final temperature, was 24.35 degrees minus the initial temperature, 21.40 degrees. And then we have to also consider the heat absorbed by the calorimeter. We know its heat capacity was 27.8 joules per degree, and the change in temperature is the same as that for the solution inside. So 24.35 minus 21.40 degrees. So the delta H then comes out to be negative 711 joules. And that's the heat from this particular experiment. What we want to do, though, is express this as not just joules for this experiment, but kilojoules per mole of reaction. Now, to do that, I'm going to use that same approach before. We hopefully recognize that this was also a limiting reagent problem. I'm going to use our little formula, moles equals C times V, converting your volumes to liters before you do that. You should end up finding that there was 0.0125 moles of sodium hydroxide in this experiment, and there was 0.0150 moles of acetic acid. Now, because they react in a 1-to-1 ratio, the base has one hydroxide, the acid has one hydrogen, you might just do some mental math and note that the smaller number will be the limiting reagent. But let's just remind ourselves of the reaction. Sodium hydroxide plus acetic acid makes sodium acetate and HOH, water. So there's the neutralization reaction, and again there's the 1-to-1 ratio. To find the limiting reagent, pick one of the two reactants. I'll take the sodium hydroxide, 0.0125 moles of sodium hydroxide, and ask yourself, how many moles of the other reactant would we need to use that up? So the ratio is 1-to-1, so 1 mole of sodium hydroxide needs 1 mole of acetic acid. So just like our mental math told us, we would need 0.0125 moles of acetic acid. Do we have that much? That's how much is needed. We have 0.015 moles, so we have excess acetic acid. Therefore, the sodium hydroxide is limiting reagent. Okay, that's what we figured out just looking at it mentally. So therefore, I'm going to take my 0.0125 moles of sodium hydroxide and switch from moles of sodium hydroxide to moles of reaction. In our balanced equation, there's only 1 mole of sodium hydroxide, so that's a 1-to-1 ratio. So we get 0.0125 moles of reaction. And now we can take the heat from our experiment, negative 711 joules, switch the joules to kilojoules, and then divide by moles of reaction. 1 kilojoule is 1,000 joules, and we have 0.0125 moles of reaction. And so, after all of that work, we end up getting negative 56.9 kilojoules per mole of reaction as the enthalpy of neutralization, the molar enthalpy of neutralization for that reaction. Alright, so there's a variety of calorimetry questions, from the straightforward physical science kind of questions, finding a specific heat capacity, for example, all the way into using it to estimate delta H's, to measure delta H's for reactions inside the calorimeter. Right? Delta H can also be calculated, we know, from tables of heats of formation, and also can be measured or estimated using bond energies. So realize you have 3 basic tools, four basic tools to find delta H's for reactions. Delta H can be found using calorimetry in experiments like this. It could be done using heats of formation and tables like we have in our data booklet or the appendix of your textbook. It could be done using Hess's law. If you have a series of chemical reactions for which you know delta H, you could then manipulate those equations and get delta H that way as well. So several different ways, and then finally by estimating delta H using bond energies as well. So those can all be interrelated questions on an AP free response question for the chemistry exam as well. So make sure you practice all 4 approaches to finding delta H.